Okay, this is a video about magnetic force, which is the next segment. And this is a shout out to pop culture references and magnetism, which looks just like what you made. It's on the cover of the Metallica album. So there you go. Now you understand this pattern and why it makes this. So you can even tell me where the poles are if you wanted to. So, magnetic force is basically the force between two magnetic fields interacting. If there is a magnetic force, both things have to be magnetic somehow. And so when we start thinking about this, then we can think about all the things that can actually generate a magnetic field will be able to have a magnetic force. So obviously a magnet has a magnetic field and so can have a magnetic force. A wire or solenoid has a magnetic field, just like we learned in class. So that means those can have magnetic forces, and moving charges actually have magnetic fields too. So a moving charge will actually experience a force. And this is also evidenced by the fact that current is made up of moving charges called electrons. So moving charges generate a magnetic field. So if you have a charged particle in a magnetic field, then you will have a force on there. And in fact, charges are not attracted, stationary charges are not attracted by magnets. A magnetic field exerts a force only on a moving electric charge, both positive and negative. And if you're stationary, you feel no magnetic force. And so again, in class, I kind of talk about how it's like a boat on a lake. If it's still, doesn't make a wave. But if a boat is moving through the water, it has like a little wake behind it as it makes waves behind it. So only moving electric charges make a wave, a wake in its path, which we call a magnetic field. So here's a diagram, which you may want to pause this video and sketch it before you move on. But in this diagram, the magnetic field is pointing out of the paper because all of the magnetic field are dots, okay? So over here, we have a positive charge, which is not moving, therefore has no force, and that's why it's just stationary, okay? Here you have a neutron, that's what the letter N stands for, and a neutron is not charged. And so even though it's moving, you can see the vector. Even though it's moving, it has no charge, so it has no force. Over here, you have a positive charge that is moving, okay, but it's not inside the magnetic field, and so there's no force. So you have to have a moving charged particle that is inside a magnetic field, and if you have all of those, then you will actually get a force. And so you have your initial velocity, and the force is directed this way, and you actually notice that it becomes a curved path. So why a curved path? Because in fact, all particles, if they are charged moving through a magnetic field, follow a curved path. And so this is just the same reason that the moon follows a curved path around the Earth. And that is because a force is always towards the center. And if you remember from rotational motion, that is called a centripetal force. And centripetal forces cause circular motion. So just like the gravity is always pointed toward the center of the Earth and causes the moon to orbit in a circle, a charged particle, like an electron, will always have a force pointed towards the center or towards the center of some sort of circle and moves in a circular path. And this isn't always a perfect circle. Sometimes it will kind of spiral in on itself, or sometimes it'll make like a helix shape as it goes up, but it'll always be somehow curved because the force will always be pointed towards the center of some sort of curved path. Okay, another thing to note is that opposite charges go in opposite directions. So if you have a magnetic field going into your screen, like this X, okay, a proton is going to curve opposite of an electron. That's because they're charged oppositely. So opposite charges go in opposite directions. That should be pretty common sense. Okay, to calculate the force that a charge experiences is QVB. And so the force is in newtons. Q is the charge, and we're going to use little q is usually when you see it. Okay, so Q, little q, and that charge is in coulombs. V is meters per second, velocity, and B is the magnetic field, which is in a unit called Tesla. So the force on a charge is the charge times the speed or the velocity times the magnetic field that it's in, which is why there's only a force if you have charge, velocity, and magnetic field. If any of these are gone, like a neutron, or not moving, or no field, that's why there's no force. Okay, so because a wire that has a current through it also has charges moving through it, that means that a current carrying wire is also going to have a force on it. So because this current is initiating or creating a magnetic field, this magnetic field will be attracted and repelled by other magnetic fields too. So here you have two magnets and a wire in the middle. And if the wire is going up, it's going to create a magnetic field that is counterclockwise, kind of going around like this. Okay? So what's going to happen then is that the magnetic field of the wire interacts with the magnetic field of the magnets, and it's going to cause the wire to move into your screen. Okay? And if two wires have the same current in the same direction, they will also attract because each one is making its own magnetic field. This magnetic field is out of the page and this one is into the page. If you use your right hand rule, you can prove that. Okay, which makes this kind of like a south pole on this side and kind of like a north pole on this side, so they are going to actually pull together and attract. Okay, and so all of this is really controlled by your second right-hand rule. And so your second right-hand rule is you put out all three fingers, kind of making like a corner of a box, where each of them are pointed in a different direction. Okay, your thumb is the force, your pointer finger is the current, and magnetic field is your middle finger. The way I always remember this is because current is the direction that the particles are traveling. So usually when you point, you're talking about where something is going. So when you point with your index finger, that tells you where something is going. Oh, don't see that. Okay, and then your force is your thumb, because the force is the strongest finger in your hand. So that makes sense that the force is the thumb, the current is where you're pointing, and then magnetic field is your middle finger, because at some point in this unit, you're going to get frustrated enough that you just want to give magnetism the middle finger. And so that's how I always remembered it. Okay, and because electrons and negative charges move oppositely, you can use your left hand to use for negative charges, since it's going to be the opposite of a positive charge. So you can use your right hand for positive charges and left hand for negative charges. And we're going to practice this on Friday. So here's an example. Okay, you have a magnetic field traveling to the left, and you have a current in a wire, and you want to find the direction. I don't know why B is there. You want to find the direction of the force on the wire. Okay, ignore the B right here. That shouldn't be there. So if you have a current in the wire going up and the magnetic field, you want to find the force, you use your right hand. So your index finger should point upwards with the current. Okay, then you turn your middle finger to point left with the magnetic field, and that should leave your thumb pointing directly at you. Therefore, that means the force is out of the page towards you. And if you wanted to draw that, you would draw a dot and then the letter F for force. Okay? So that is the end of this video. Come in on Friday, and we're going to practice and have lots of fun.